Hello, everybody. So welcome to the first Python Data Science Meetup of 2016. Woo! So I appreciate it. Thank you. I don't know how these things work. Going to get just a few small things kicked off. Quick show of hands. How many of you are on the datascience.la mailing list? Okay, most of you, happy to hear it. For those of you that aren't, at some point I'm going to get tired of copy pasting the message to the meetup boards and all that, and the only place I'm going to send the meetup information is the datascience.la mailing list. So eventually you're going to want to get on that. So I had a couple of other things. There's the first meetup. We've got a second meetup scheduled, not for the Python Data Science meetup. We have a meetup scheduled for next Monday. If you want to go, it's on the west side. It's at ms.com, and it is. We have an Apache maintainer who is one of the main architects of Apache Tahoe, and he will be speaking about basically how they're building a high-end columnar distributed data store on HDFS and whether such a thing is even possible or not. So that's next Monday. You can still sign up on Eventbrite. You can find out about it on our website, which is datascience.la. So the next thing I wanted to do is we have somebody from UCLA to talk about UCLA's DataFest. So if I could call her up. So real quick, DataFest is a thing that I've gone to now 2 years. It's super fun. You should do it, but I'm not going to steal more of her thunder.
Hi everyone. Hello. Okay, I would like to introduce myself as the undergraduate committee member of the 6th annual DataFest hosted by UCLA. And DataFest is a weekend-long data analysis competition structured like a hackathon, but differs as teams from local universities work with the datasets to provide tangible business insights from the data at hand. Last year was our largest event to date, and we hope to emulate the success again this year. As a non-profit statistics club coordinates this event, we really appreciate and acknowledge corporate and private sponsorship and support as an integral part of our program. Sponsoring DataFest gives your company the opportunity to share its brand with some of the highest achieving students in Southern California. Teams will represent UCLA, USC, Cal Poly Pomona, Cal Poly San Luis Obispo, Cal State Long Beach, UC Riverside, and possibly more. Though we appeal to individuals with statistics background, we also attract students from business, economics, accounting, and social science departments. Bring a diverse host of talents to our event. Previous competitors have gone to hold analytics auditions at high-profile companies like LinkedIn, Salesforce, Deloitte, Experian, and more. Our sponsorship will be given an opportunity to share promotional and recruiting materials and swag during the event. So if your company is interested in DataFest and want to take advantage of this opportunity, please feel free to get one of these papers with all our information, and I will put those in the back of the table so you guys can grab it. Thank you so much for your time, and I really appreciate we can work together. Thank you.
Can everybody hear me without magnification? All right, good. So I want y'all to look around what a really cool venue we're at. Like we're at the Venice Art Center in Lincoln. This is really cool. This isn't like when I lived in Nashville, Tennessee, meetups weren't happening in awesome spaces like this. And the reason we have such a cool space with great food, I know we even have veggie trays, which is amazing for a meetup, is because of our sponsors. I wanted to thank Open Mail, and I wanted to give them an opportunity to say something. So thank you, Open Mail.
Hey everybody, just want to thank everybody for coming out. At Open Mail, we share the interest of promoting Python and data science and the intersection of those two within the community in Los Angeles. So we're really happy that everybody's been able to come out, and the PyData meetup's just been growing by leaps and bounds. One of hiring. So if anybody is looking for if anybody's looking for a collegial environment, Python data stack, and a lot of great people to work with, definitely grab anybody who you see as an OpenMail name tag on and ask them about OpenMail. Thank you.
All right, so we're going to get now to the real meat of this meetup. Real quick show of hands, y'all came here. Have you used H2O? Are you familiar with H2O, or is this brand new to you? Okay, so you've got a lot of new people to teach. Pretty excited. So we're very lucky. So Erin LeDell is a statistician and machine learning scientist at H2O. She's the main author of H2O Ensemble. Before joining H2O, she was the principal data scientist at WISE and at Marvin Mobile Security. She's the founder of Data Scientific Incorporated. She has a PhD in biostats with a designated emphasis in computational science and engineering from UC Berkeley, a way better school than I could ever get into. Her research focuses on ensemble machine learning, learning from imbalanced binary outcome data, influence curve-based variance estimation, and statistical computing. So everybody give her a warm welcome. It's Erin LeDell.
All right. Oh, yeah. Okay. All right. Thank you for having me. I came all the way from Northern California, where it's equally as rainy. I had this dream that I was going to come to Venice Beach and it was going to be beautiful. And it's, it's still beautiful. Yeah. So yeah, I guess it's good that we're getting rain in California, so I shouldn't complain. So anyway, so this is intro to H2O and Python. So presumably a lot of you guys are already using Python, and maybe if you're doing machine learning, you're using like scikit-learn or some of these other libraries that are popular. So hopefully by the end of this talk you'll have an idea about what H2O is and how it compares to maybe what you're already using. And then, so the first half of the talk will be slides, and then I'll go through an IPython notebook, and I'll point you guys to where that is, and if you want to follow along and do the IPython notebook on your own machine, you can do that, or you can just watch and take it home for later. So. Okay, so I already got an introduction, so I won't really talk about this stuff too much. And before I forget, I just want to grab my phone so I can time myself. Make sure I don't talk too long. So anyways, yeah, so I work at H2O. I've been there for about a half a year. So I recently graduated from Berkeley in May. So, but kind of before that, I had another career as a computer programmer, and before that, I was a mathematician. And then I, learned about machine learning, and then my whole life has just been about machine learning, basically ever since, because I love it so much. So I am sort of more of an R person. I hate to say an R person or Python person, because I think we're beyond that at this point, but I'll say as a statistician, I was using R a lot for the last 4 or 5 years, but the first language I ever learned was Python, so I've kind of been using both for a long time. All right, so what is H2O? So first of all, there's H2O the company, and then there's H2O the software. The company actually used to have a different name. We used to be called Hexadata, which was spelled 0xData, which nobody could pronounce that, and it was just, I don't know, people didn't like it. So anyway, we changed our name. Now we're just H2O, and so we've been around since 2012, and we're based in Mountain View, and the sort of people that started it were loosely affiliated with Stanford, but there were some people from Purdue and kind of these mishmash of people that came together and started this company. So H2O, the software, is open source, and that's probably the main reason that I work at H2O. I'm actually not very interested in any non-open source software at this point. I think that's like the old way of doing things. So that was really important to me, and I don't know if you guys are that passionate about open source as much as I am, but that's a big win for me. So it's open source. We try to make it easy for people to use, and part of that is that we make APIs in R and Python. There's a Scala API. It works on Spark and Hadoop. So originally it was written for Hadoop because Spark didn't exist, but then Spark got popular, and so we actually rewrote all of H2O from scratch so that it would work better with Spark. And that was H2O 3.0, which was released over the summer. So that's probably that, some of you are actually, nobody really raised their hands, did you? Anyone who used H2O? Okay, so anyway, if you were using H2O 2.0, there were some changes that we made, and so it's a little bit different now. But so the last thing is we also have a web interface. So if you really just have a hard day and you just don't feel like writing any code, you can just click and do everything from the web, the same as that you can do from the different APIs. And so the whole point of H2O is that it's not just like another, scikit-learn or another machine learning library. The whole point is that we've rewritten all of these algorithms from scratch so that they work in this distributed framework. So I'll explain more about that later. So I just wanted to mention just a couple more things about the company. These are the founders. Are there any Java people in here, or people that identify with Java in any way? No? Okay. Then if you did this, apparently Cliff, I'm not really from a Java background, but apparently he's a famous Java person. And so if you were a Java person, you might know him. But he's sort of maybe like if you're an R person, the Hadley Wickham of Java. I don't know. I don't know who the Python equivalent would be. But anyway, he basically did a whole bunch of research that made Java actually be performant and fast. So in the 90s, he got Java to work, and so he developed the Java hotspot compiler, which is kind of a new way of doing things. So he's sort of like the brains behind all of the underlying architecture to the system and why it's so fast and why it's good. So, and then if you do have any sort of machine learning background, you might be familiar with some of these names. So Trevor Hasty and Rob Titrani have a famous machine learning book that's called The Elements of Statistical Learning, and they have another one that I think it's called like Intro to Statistical Learning or something like that. So they're pretty famous in the machine learning community. And then Dr. Stephen Boyd, he's famous sort of like for different things, but he's more of an optimization guy. So these are our scientific advisors. We work with them to make sure, so we've implemented a lot of their algorithms, and so we work with them to, make sure everything is sort of legit. All right, so here's the agenda. I'm just going to explain what H2O is, and then I'm going to talk about the Python module, and then I'm going to do the demo. Okay. So I've already explained this a little bit, but this is kind of like the high-level summary. It's H2O is written in Java, and that's one of the reasons why it's fast. So typically, high-performance machine learning libraries are either written in C++ or Java, maybe some other languages as well. And essentially, how it works is let me get to that. I don't want to get ahead of myself. So anyway, APIs in R, Python, Scala. All right, so the whole, this is just kind of an overview slide. So the whole point is that, you shouldn't have to sample your data. You have all this big data that, you've probably spent a lot of time getting, and then what ends up happening is that people have now too much data and they can't train their models, and so you end up sampling out of this big data, so you don't really have big data anymore. So the idea with H2O is you don't have to sample your data, and then part of our other philosophy is that we want to have all of the sort of cutting edge algorithms. So a lot of the machine learning algorithms have been around for a while, but there's lots of different things that, lots of developments that get added over time. So there's maybe new optimization methods or new ways of parallelizing things. So we're always trying to have sort of like the cutting edge of the algorithms that are out there. So here's just sort of an overview about the algorithms that we currently have. So it's kind of a smattering of different things. So we have mostly supervised learning algorithms, but some unsupervised stuff. We have kind of like what I would call like the big four like algorithms that people use a lot. They use random forest, GBM, gradient boosting machine. GLM is still really widely used, and deep learning. So we have a function called deep learning, which I think probably could be more aptly named to like say what kind of deep learning it is, because there's all different types of deep learning algorithms. So it's a multi-layer feed-forward neural network. So I don't know if that, if any of you guys are familiar with all the different deep learning algorithms, but basically this is one that works well and works fast on CPUs. So deep learning, a lot of the stuff is written geared towards GPUs right now, and so this is one that still actually works really well on the CPU and is quite fast. So maybe just a couple other things. So we have a lot of different solvers. So something that we like to do is have different optimization routines that you can use in each of these algorithms. So we don't just make you use a particular one. And if some of you are familiar with R, there's somebody called Matt Dowell who writes a package called data table. And data table is sort of like a replacement for a data frame in R, and it does really fast things like sorting. So there's something called a radix sort, which is really fast. So Matt Dowell now works at H2O, and he's making like a distributed version of this. So you can do distributed sorts really fast and stuff like that. So if you're more on like the munging side of things, that might be interesting to you. Okay, so here's just sort of the idea behind the distributed part of H2O. So there's something which we'll call the H2O cluster. So rather than thinking about the H2O cluster as like a physical machine cluster, just think about it as just like this abstract thing that floats across machines. So it's code, it's Java code running across a bunch of machines, and that's what we call the H2O cluster. So the idea is that there's a shared memory model. So all of the nodes through H2O can access all of the data that's spread out across the cluster. So all the computations are in memory, which is similar for other machine learning software. Each node only sees some rows of the data. So I should mention you can also use H2O on your laptop, which is like 95% of the time what I'm doing, because usually I'm writing code and I'm testing it. I'm not probably running huge data sets all the time. So if you start it on your laptop, it's just like a mini cluster on your laptop. You don't have to do anything different or change your code or anything like that. It just, wherever you start H2O, if you start it on a machine on Amazon with like let's say a multi-node cluster, then you see H2O as the same thing regardless of how many nodes it's on or how many cores you have on your machine. So, but the idea is that you can do machine learning on data sets that are larger than the memory for one machine. So that's why we split the data across all the machines. And so we have, the last point here is I'll describe sort of the H2O frame, which is a distributed data frame. And so the middle point, so how does this all work? It's basically just a big distributed key value store. So everything has an ID somewhere, and so a model has an ID, a data frame has an ID, and basically just everything is organized throughout the cluster just by IDs. So that's not super important, but just something to mention. And so I said I would explain the H2O frame. So this is our equivalent of a data frame, or like in Pandas has a data frame. R has data frame, so everyone has data frame. So this is our data frame, and basically it's just like I said, a distributed data frame that goes across all the nodes. And all of the syntax to work with the data frame is, for the Python module, we've implemented so that it will work like a pandas data frame. So if you've already learned how to use pandas, then using H2O frames should be pretty easy. We haven't implemented every single thing that you can do on a pandas data frame, but most of the stuff that you would need to do, subsetting columns, picking things out, doing, all sorts of munging stuff can be done on H2O frames. Okay, so let's see. And then when I said just sort of imagine the H2O cluster as this like nebulous thing that is across physical clusters, this is kind of like just a diagram of that. So your data could be just, let's say, a CSV file on your machine, or it could be in HDFS already distributed, or it could be in S3. There's a lot of different places your data can live. And H2O is kind of designed for using on Amazon, or using on commodity clusters, I guess I should say, not necessarily Amazon, but just the idea that rather than trying to design something that works really well on a single machine, like say a single very expensive machine with a lot of RAM, we designed it so that it could work cheaply across a bunch of nodes. So that's kind of the philosophy behind it. Okay, so if you want to download the H2O Python module, this is how you do that. And if you did feel like you wanted to follow along later, you could go ahead and go to this website and look at and basically copy these commands. So there's a couple Python requirements, which it's not on the next slide, but I'll mention those. So basically, you just pip install this H2O package, right? And then this is where our code is located. It's a little cut off, but it's H2O.ai H2O-3. And so all of our code, as I mentioned, it's open source, so all of it is on GitHub. And we do all of our development in the open. We actually use Jira instead of GitHub issues to track everything, but if you click on our Jira, you can see basically everything that we're working on, and all of our discussions about that. It's very open. It's kind of a little bit strange to work in public, but I've gotten over that, and I kind of, it's nice, I guess I'm kind of just a private person, so it was weird for me to be, working in public, essentially. That was TMI, you didn't know. So anyway, this is our GitHub. So there's different ways that you can download H2O. You can clone the repo and build it yourself, or you can just download the jar and not use any of the APIs. When you download the Python module or the R package, it will download the jar for you, the H2O jar, and so you don't have to do anything behind the scenes. It's not any more complicated than just having, any other package be installed. So all you need is Java on your machine, basically. Okay, so this is H2O and Python. There's lots of these talks that we give. So if you're for some reason got confused and you're actually an R person and you hate Python, there's different versions of these slides there's like an R one and stuff like that you can find on our SlideShare website, which at the end of the talk I'll give you the link for that. But this is for Python. So the requirements are basically, Java 7 or later, Python 2 or 3. We, I guess, somewhat recently added Python 3 support. And I mentioned there's a couple Python module dependencies. And it works on Linux, it works on everything. A lot of our support requests are from Windows, so I think it works better on Linux, because maybe there's one person in our office, Cliff, Click, one of the co-founders who has a Windows machine, and so, you know, I mean, we do test it on Windows machines, but he's, all of us are always testing it on Linux or Mac, so the bugs come up more quickly. All right, so I already talked about how to install it, and then this is just a little bit more about the design. So the idea is that none of the computations are ever being done in Python, and none of the data is ever being pulled in. Well, technically you can pull the data in and out of Python, from Python to the H2O cluster, but you don't have to. So the idea is if you're trying to be efficient, you don't have to load it into your memory in Python and then push it over. Although you can do that if you wanted to do some, you know, something like that for some reason. Okay. So here's kind of, this is some screenshots from the IPython notebook that I'm going to go through in a bit. So this is how you start H2O. So if you're used to modeling in Python or R, basically you load a library and then you load some data and then you train a model. So the only extra step that you have to do here is you have to start the H2O cluster. So you do that with H2O.init. And what it will do is if you don't already have a cluster running on your machine, so by default, you'll see right there it says no instance found at IP and port localhost. So those are the default arguments for H2O.init. It will look on your local host at that particular port to see if H2O is running, or on whatever port you put in the arguments. And if it's not running, it will then start an H2O instance, or an H2O cluster on its own. So right here it's saying, okay, you don't have that running already, so I'm going to start one myself, and then it starts the cluster. So that's the only really extra overhead, is that you have to actually start the H2O cluster. And so then it will start it and then hopefully say successful. So this is if you've already have one running somewhere, or let's say you were working on your H2O cluster and then you go off and do something and come back later and it's still running, then you can reconnect to it. And so if you do H2O init, it will look and see if there's something running, and if so, it will just print out some information about the existing machine. So, all right, so this one you see, this is on my laptop, so this is, 8 cores, and the default cluster memory, I think, is set to 4 gigs, so you can change that. So that's basically in Java, the XMX argument is the same thing. So if you want to start, actually, I think, I'm not sure about this, but I think if you started on a much bigger machine, the default will be different, but I can't remember. So basically you can control your memory if you want, but it should basically use everything that's available to it. Okay, so I'm sorry if you can't see this very well, especially in the back, but actually, why don't I'm going to give you guys the URL to the IPython notebook right now, and if you want to follow along as I'm sort of going through these slides, you can do that. So, let me just skip ahead to where I have that URL. So, it's if you go to our GitHub, the H2O-3 GitHub, there's a folder called H2O.pi. And then there's also an H2O.R, and they look very similar. So then there's a subfolder called demos. And the demo that we're going to be going over in a little bit is called H2O tutorial EEG iState. So we're going to predict whether your eyes are open or not based on EEG signals. So if any of you guys want that, I'll leave that up there for another second or two. So the one other time that I gave this demo, everyone started downloading the data set at the same time and broke the Wi-Fi. So the data set is not that big. I think I don't know how many megabytes it is, but it's like 100, maybe 14,000 rows and 15 columns. So small. But people were also Git cloning H2O, which is about, 40 or 50 megabytes. Is the jar. So anyway, if you were going to do that, you might want to start now. So I don't know how their Wi-Fi is here, but, all right, so let me just go back real quick. So we started H2O already, okay. So yeah, this is unfortunately very small. Okay, but I'll assume that if you want to read those words, you can go to the IPython notebook, and this is midway down. So basically, we wrote the H2O Python package to be as similar to scikit-learn as we could, because I think it's actually a very good package, and we wanted to kind of have like a seamless way that people could sort of use all the same, I want to say like programming paradigms from scikit-learn. So we actually spoke to the scikit-learn people at length, sort of like about our API when we were writing this for the first time, and asked them, is there anything that you would have done differently, or, because clearly it's been wildly successful, and so we were trying to sort of get any tips or tricks about like what, how did you make this work so well? And the one thing that, so it was Andy Mueller, I don't know if you guys know who that is, but it's one of the main devs for scikit-learn. So the one thing that he said was at the time that he created scikit-learn, pandas was not around, so there were NumPy arrays and stuff like that. So the one thing that he said he would have done differently is be able to, instead of passing along like the whole data frame as the argument for like your X and your Y, he said he would have, first of all, rather been able to specify the columns that you want to use as predictors just by name, so column names, and that wasn't something he could do at the time, and so that was basically the one bit of advice, and so this is something that we were already doing with our API. So we have, actually let me get more into that in a second, and we'll just talk about importing the estimators themselves. So basically, so from h2o.estimators.gbm, we have this is our GBM. It says H2O gradient boosting estimator. So the process here is that you first sort of set up the model. You make an object called model or whatever that's of class H2O gradient boosting estimator, and then you set up the model parameters at this stage. So you say, I want this many trees, I want the max depth to be this, or whatever. You can specify different distributions. Our GBM actually has a lot of distributions compared to some of the other implementations. So we basically have all the distributions that we could think of implementing, including like Tweety and, well, a lot of things already have Poisson, but so basically, so a lot of different distributions you can select. So that's setting up the model, and then to actually train, then there's a train method. So model.train, and then X and Y. So X would be your list of column names that represent all of the columns that you want to use in your H2O frame, which would be called train in this case. And then Y is just the name of the predictor column. So you can also specify by index or name. So what else could I say? So basically we have, so something I was sort of getting used to when I came over from R and Python modeling was we named these two arguments training frame and validation frame. And so I think sometimes people get confused about like the validation frame argument. So essentially in modeling, you don't always have to have a train, a test, and a validation set. You can maybe just have a train and a test set, or if you're doing cross-validation, you could just have a training set. So we kind of, we built it so that, if you do have a train, test, and validation set, there's places for all of those things to go. So the idea with that is, if you want to do tuning, you might set aside a little validation set and train your model, train and validate it on the validation set, and then once you've selected your best model or something like that, then you have another test set, and then predict on the test set, and then evaluate the final performance of the model. So that's what we mean by validation frame there, but if you do just want to do train and test, you can put a test set there. It's just going to be called validation frame. So anyway, that's just kind of, I don't know, in machine learning there's a lot of terms that are kind of like sort of loosely defined or defined differently to different people, and I think validation frame or any sort of stuff about validation gets a little, people have all different ways that they think about that. So anyway, so then after you type model.train, it'll train the model. So, and then, so this is just part of the printout that you would get if you printed the model object after it trains. So this is a GBM, so it's printing out some of the GBM parameters there. So number of trees, let's see, model size and bytes, a bunch of stuff about the trees themselves, and then it will report out metrics. So the first metrics that it will print out is the training metrics. So usually that's not what you want to look at. You probably want to look at the validation metrics or the cross-validation metrics if you do cross-validation. And I'll show you how to do cross-validation and grid search and a bunch of other things in the IPython notebook. But this is just sort of the vanilla case. So you can see, okay, so this was this example was a binary classification problem. And by default, we'll print out all the metrics that you might care about. And if it's a binary model, you might not care about MSE or something like that. Maybe you want AUC, and that's the only thing you care about. But we compute them all by default, so you get them for free, I guess, essentially. So, and then you see below there's a confusion matrix, so you might be wondering, well, how do we decide what the threshold is for making that decision boundary? So you can specify that on your own or change it after the fact, but basically we take whatever threshold is the threshold that maximizes the F1 score is what we choose by default, because we had to choose something, I guess, so that's what we chose. So you can, this is sort of your, the default printout, and I'll show you guys more of that later. So, okay, let me see how I am doing on time. Okay, good. All right, so this is a demo with EEG data, and it's from this device called an emotive. Have any of you guys heard of this thing before? Emotive? Yeah. Okay, one person. So basically, it's this sort of plastic spider that you put on your head that, it looks like a spider, but so with EEG data, you can get really good signals if you either put the sensors like in your skull, which is not super convenient, unless you're like a really hardcore quantified self kind of person. Or they have these like gel things that if you were to be in a study or something like that, they're still over the skull, but they're a little bit more medical grade. And then so then there's now this company. I think there's a number of different companies kind of like this, but this is sort of like the consumer EEG device. And it sounds very promising because I think, I'm just going to wear this all day at work and like see like how, what music makes me like angry or emotional, or when am I like happiest or something like that. I had a lot of like ideas about this, but I think unless you're bald, it doesn't work that well. And I thought I was just stupid or something, like not knowing how to set it up, so I actually bought one of these things. And so it doesn't work as well as I thought it would, and apparently other people on the internet also think that, and maybe we should have done more research before buying something like this. But anyway, so I don't think it works that well, which is unfortunate. But somebody was able to make it work, and maybe that was a bald person. But so they released a data set, and basically what they did was, I guess your brain waves are very different whether or not your eyes are open or closed. So they had made a training set where they just marked the times where their eyes were open and when they were closed, and then the idea is to train a classifier to detect this. it's not a very useful thing, but I thought it was kind of interesting data. So anyway, this is the machine learning problem is to predict whether or not your eyes are open or closed. And this is data from the emotive neural headset. So it has 14 channels and 14 of these little things that kind of sit on the device. And so this data set is from the UCI machine learning repository, which I don't know, a couple of years ago I kind of given up on that because the data sets are so little, but I don't know, in the last 2 years I've been seeing more interesting data sets popping up there, and this is one of them. Well, I don't know if it's that interesting, but it was unique. Okay, so first I'm just going to mention what flow is. So flow is the name of our GUI. So if you start up an H2O cluster, either from the command line in Java or from Python or R, it will start this web server in the background. And you just go to localhost port 54321 by default or wherever else you set it up, and it will bring up this web interface and called flow. And so there's so I was a little I don't know, judgmental of flow when I first saw it. I was like, what is this? Nobody's going to use this. It's crazy. Why wouldn't you just write the code? It's so much easier. But it's actually not easier to write code, it turns out. It's easier to click on buttons. So, so I actually use this every now and then. So usually my workflow is I will start a cluster from probably usually R, and then I would load my data, and then maybe I open up the browser and sort of explore the data a little bit. And so what one of the things I like about H2O is it sort of does all the things that you would probably do in your workflow automatically. So, one thing you want to do with a new data set is look at the data and see if there's any weird stuff going on, or any issues that you need to be aware of. So, so you can view these column summaries. You can look at, let's see, it says if there's missing data, how many zeros, which I guess, I don't know, would be useful sometimes, whether or not there's, I guess, infinite values, although I don't think I've seen the data set of that. But then min and max and mean, if it's so there's different data types, in all languages, but in Java, the sort of categorical data type is called an enum, and in R it's called a factor. What is it called in Python? Does it have a name? I don't know. There's probably a name for it, but basically when you're doing machine learning, you need to know the data types, because you might have something that's coded with 1, 2, and 3, but that might actually represent groups instead of numbers. So if H2O sees numbers, it will assume they're numbers, but you can, unless you specify in advance what they are. So you can do that when you load the data in, or you can do it afterwards. So usually I do a lot of binary classification problems. So I will load it in. It will usually be coded as zeros and ones, and then I either in R or in Flow, you can just click this convert to enum thing here. And then that will convert in this case, this is the outcome, the eye detection. You can't see that, but there's a column here that's called eye detection, and that's a 0 and 1. And so right now it's marked as int, and so I would just click that button and it would do the conversion under the hood. So the reason that we do that is because it's from a data perspective, it's more efficient. So if you don't need to store it as floats or ints, then you shouldn't be doing that. So if you have really, really large data, maybe you could notice a difference, in the speed or whatever. But so we've actually talked about this a little bit, because sometimes people don't know to think about data types, and that's not something that people who are at least new to machine learning or data science think about that much. Maybe they don't have a computer science background, so they don't think about that type of thing. So we've talked about do we want to, basically right now, if you try to train a classification model and it has numeric data in the outcome, it will say no. It'll be you can't do this, you need to convert it to whatever. So we've talked about, maybe afterwards, if you guys have any opinions, or if you have opinions later on about this part. But I kind of, at the company, have the role of basically like making sure the API makes sense and is usable and like works for people. So this is one of the things that I've been wondering about. Could we make this easier if we kind of like don't make the user think about what the data type is? Because a lot of times on our, we have a Google Groups where people ask questions. They say, I trained this model and it's, where's my, ROC plot? I thought, whatever, but it's like they accidentally trained a regression model and we don't want that to happen. So anyway, that was a little bit of a sidetrack. So, so this is what it would look like in Python. So if we, so data would, this is after I've loaded the data, which I'll show you how to do in the notebook, but we have things like data.shape that will print out the dimensions. Data.head will print out the head of the table, so that's what it looks like. For this particular data set, I added a column called split so that regardless of what platform you're using or anything like that, there wouldn't be like confusion about what. There would just be one example of like a train, test, validation split that you could use just to make it easier to sort of benchmark on all the different platforms. And I just noticed that if you don't do something like this, then you say, oh, we'll just set a seed and then it'll randomly choose and then we can decide on the seed, but then if we go over to R and then it has a different seed, like, anyway, so I added this column to make that easier. Okay, so now we'll start the demo. So this again is the URL for that. And I don't think I've actually run this myself, but somebody else made a scikit-learn equivalent. So basically everything is done exactly the same, but in scikit-learn. So that's also in the demos folder, and you can check that out if you're interested. Okay, so we'll pause there. Okay, so just if you're not familiar with Jupyter notebooks, this is a Jupyter notebook, and I'm sure most of you guys are familiar with this, but if this is the first time you've seen it, it's basically just a web interface where you can type in code and it will execute the code on your machine and print out any results. And so it's nice for sort of doing interactive analyses, or if you have a lot of plotting that you want to do or something like that. It's also good for teaching. So that's why I chose to do this. So also, if you didn't know, Jupyter used to be called IPython Notebook. Now it's called Jupyter Notebook, and Jupyter stands for Julia Python R, which I heard a few like, oh, that was my reaction when I figured that out too. I was like, oh yeah, that makes sense. Okay. But it was a really long time before I knew that. That's why I like to tell everybody. So anyway, so now they've rewritten the IPython notebook to have sort of, you can plug in different kernels. So there's a Julia kernel, an R kernel, and a Python kernel, and whatever other language will come in the future, I guess. So yeah, so now it's Jupyter. So anyway, the way that if you're not familiar, let me just show you real quick how to get here. So one thing is you could go to the GitHub and like navigate in our on GitHub and see the document there. Or if you wanted to actually run it on your machine, you would git clone the H2O3 repo. So right now, well, you can't probably see that at all. But basically, you would clone the repo, so git clone H2O3, and then cd into the Python demos directory, and then just type in the command Jupyter space notebook, and then it will pop up should pop up your browser, and it should give you like a list of all of the Python or Jupyter notebooks that are in the folder of wherever you executed that command. And so then you would just like scroll down to wherever it is. So it's like H2O, this one here. And so I clicked on that, and then it opened it up over here. So that's how that happened. So, all right, so this is the tutorial. And so the goal of this tutorial is just to show you how to do some basic like data manipulation with H2O, and then how to train a model, and how to do grid search, and how to do like standard machine learning things. Okay, so here's the prerequisites. I think this is up to date. There might also be, I think maybe when we added Python 3 recently, there might be the futures module. So if it doesn't work, let me know, because I think it might actually be missing a prereq. So, all right. So, does anyone want me to wait for a second while they do any installation? Okay, most people don't have laptops, so that's good. All right, so this we've seen before. So to start up the H2O, oh yeah, and actually let me just highlight this. So this is where you pip install so each of our releases, we put out a release every couple of weeks. It's actually because of like Christmas time. This one is maybe like a month and a half old, but we're putting out a new one, I think, this week. So we have major releases, and we give them all names. So this major release is called Tibshirani release, which is one of our advisors. And then, so this is 3.6 is the version that corresponds to Tibshirani. And then we have like incremental minor releases. So this is Tibshirani 8. So this means 8 times we like forgot to put something in. No, I'm just kidding. Yeah, so anyway, so we'll have a new, I think, major release coming out soon. And usually we put all the new features, and we usually add things pretty often. So this release has a lot of new stuff that the previous release didn't have, and just new features. This release, some of the big things that we added were stochastic GBM. So if you've heard of XGBoost, who here has heard of that package, XGBoost? Okay, so that's a popular package right now. I'm not sure like why it's like so popular, but I think a lot of people use it on Kaggle, and so it's people have been kind of really excited about it. But there's been a lot of, I think, confusion about what it actually is. So people a lot of times ask us like, do we implement XGBoost or something like that? So XGBoost is just the name of a package that's a GBM, so gradient boosting machine, and it has like some I guess extra features that some other GBMs don't have. So one of those things is column sampling for the trees, and I think it has like per tree column sampling rate, and then like overall column sampling rate. And so by default in GBM, like you would just sample. I'm not going to go into too many details about how GBMs work, but basically you can improve the results if you utilize this sampling rate parameter. And that's why XGBoost, I think, has become popular, is because it actually performs better, and it's a really good implementation of GBM. It is multi-threaded, but they have a different version that's like their distributed XGBoost, and I haven't played around with it, but I think it's actually a different code base, but I could be wrong. It has like a different set of docs and stuff like that. So there's like regular XGBoost, which would run on like just one machine, very fast, but then there's also a distributed version. So with H2O, all of our stuff is distributed by default. We don't have different versions. We did that once with our random forest. We had like a what we call fast RF, and then we had a distributed RF, and we ended up, when we migrated to H2O 3, we just made everything be just the distributed version, because I don't actually know why, because I wasn't there when we made that decision. But anyway, that's our sort of philosophy, is that everything should be distributed, and we're not going to probably waste time implementing things for a single machine, because there's a lot of other implementations for single machines that already exist. So that wouldn't really be adding much value. So anyway, so we're going to start our H2O cluster. So import H2O and H2O.init. So I just started this before I got up here, so now it says, okay, so an hour and 30 minutes ago I tested it. So it's been running since then, just sitting on my computer. So, okay. So the thing that you're going to need to do is just download the EEG data. And I have a copy of this on my local machine because I just don't need to use the internet if I don't have to. So, but on the one that you have in GitHub, it'll have the actual, the real URL. So I'm just going to run it from my local machine. So anyway, so there's H2O.import file, which is like very similar to pandas.read.csv or any of, basically just a standard file reader. And let's see, we support a couple different types of files. So SVM Lite or libsvm, that's a format that we support. CSV is typically what people use. And then we have all the sort of connectors to different data sources. And we also support ARF files, which I like ARF files a lot. I'll just make a statement here. So ARF files are great. I don't know if you know what they are, but there was a package a long time ago that still exists called Weka, and they came up with this thing called ARF files, and basically it's just a CSV with a header, but the header defines what all the column types are. So there's never any question about, like, if I load this in, is it going to be a string, or is it going to be whatever? It's very straightforward. That's why I like ARF. So it's good for machine learning, at least. Okay, so I'm going to parse this data. Okay, so that didn't take very long because it's 14,000 rows, I think. So we're going to just go ahead and execute all of these, even though the results are there. So data.shape, okay, still the same. Data.head. So these are just the 14, these actually correspond to 14 parts of your brain. So if there's any neuroscientists in here, maybe they would know exactly where these are. But you can also Google that. All right, and so data.columns will show you what all the columns are and print them out like that. So to select columns, like say we want to just select a couple columns, like AF3, I detection and split, let's define a list called columns, and then let's just subset like that. It doesn't really look like I'm doing anything, but I'm actually executing this on my machine. So anyway, this is the same as pandas basically. So if you want to just select a single column, let's define, so we're going to use the variable little y to represent our response in the machine learning problem. So let's call that I detection and then say data bracket y. And so that'll give you that. And so unlike pandas where the columns are actually a different object called a pandas series, in H2O each column is a frame. So basically that's just a minor difference, but so everything that you can do on a whole data frame should also work on a column. So let's look and just say, okay, like we were told this is a binary response, but who knows what you're going to get when you download things from the internet, so let's just check and look at demonstrating the unique function. Okay, so unique values are 0 and 1 here. So this is, actually I can make this bigger, I think. Okay, is that better? Okay. So this is the part where I was mentioning, like where you need to specify what the data type of your response column is, because if you don't do that, then we can't efficiently do machine learning. I mean, we could, and we've talked about sort of converting secretly if you don't specify it, or just not converting and taking the performance hit. But basically, if you're doing a classification problem, binary classification or multi-class, you're going to want to convert this to what we're calling a factor, because that's kind of like, I don't know, it's the name in R, and I guess, I don't know, maybe it is also the name in Python, but factor is the thing that represents categories rather than numbers. So basically we're taking data and taking the Y column, and then because that's just another H2O frame, it has the dot as factor method. If you apply that to that, that'll just convert this, and so we're just like reassigning data Y as the factor version of that. Okay. And so here's some other stuff that we can do, like, okay, so now that it's a factor, how many levels, which are how many categories are there? There are 2. And so that's n levels. Okay, what are the levels? Okay, they're 0 and 1. So these are other things that we might do as we're just sort of inspecting our data. So another thing we might want to do, and you actually don't have to do this in H2O, which is kind of a thing that you should know, is that when you have missing values in machine learning problems, you either have to deal with that on your own, or you have software that deals with that for you. And when I say deal with that, I mean impute the values so they're not missing anymore. So with all of the H2O algorithms, we have ways of just doing that automatically for you. You can also do that yourself if you want to do something special or impute in some way that we don't support. So anyway, this is how you would check if there's any NAs, although it doesn't actually matter. For our 2 tree-based methods, GBM and random forest, basically it just sends it down the tree and it always goes left, which is how we deal with NAs, and that actually works really well. With deep learning, we actually impute all the values, so we scale everything and we impute. I think by the mean is the default. Might be the median, I can't remember. And for GLM, we might change this, but right now we drop the rows. So that I think will probably change because it's not consistent with the rest of our algorithms. So anyway, the goal is for you not have to think about the missing data, because it's just an annoying thing that you have to do when you're doing machine learning. So anyway, this is how we would. There's a dot is NA method, and so that's just showing is it NA, true or false, 0 or 1. This also works again on a column because it's the same thing, it's a frame. All right, I'm going to skip over some of this. So here's the table method, and here's just, we're going to take a look at the distribution of the outcome, because usually if you're doing binary classification or multi-class, it's good to sort of have an idea, is this a very imbalanced data problem, because that can cause issues in your machine learning algorithms. So we're just going to take a look here and find the proportion of each of the classes. So I think, was it 0 is on top, so 0s is 55% and 1s are 44%. So that's fine. Okay, so the next part is, okay, so this is just how you subset columns. So what we're going to do is we're going to take our data object and create the train, validation, and test set. And this is part of the reason I added that column, is because this is very easy to do if we do it like this. So I'm just saying subset everything that in the split column is identified as train. We also have a split frame function. So most data sets don't come with that already identified, so you can chop up the frame and make a train and test on your own as well. Okay, so now we're finally to the point where we have our data all prepared, and we're going to do train a GBM. So this is code that you saw before. Maybe you can actually read it this time because it's a little bit bigger. Let me stop for a second and ask if anyone has any questions. Okay, am I going too fast or too slow? Okay, I'll just check my time again. Okay, I'm going to try to hurry up. All right, so this is how we train a GBM. We're going to import that thing. We're going to set it up, just defining our parameters. All right, so remember I said X is just the list of column names or of indices of your predictor columns. So I'm just going to say, let's let X be train.columns, which would be everything, and then maybe let's just like delete the last two, which is eye detection and split. So we'll just do that. So there's our X columns. We already defined Y earlier, so we don't have to do that again. So here we go. We're going to train a GBM model. So this is just 100 trees, 14,000 rows. So it only took a few seconds to train. All right, so now all of that's being done in parallel because I have a 8-core cluster on my laptop. Okay, so now we've trained the model. So this is what we saw before. If we just print the results, there we go. And then, so I'm interested in the AUC. Okay, that's like decent. Actually, these are the training metrics, which come first, and then they have validation metrics below. So AUC is a little bit lower, 0.92. And then there's all sorts of other stuff. So this will all print out by default. Well, if you type print model, it will print out. So there's something, for all of our algorithms, we have a scoring history. So there's some idea of like progress over time. So with the GBMs, it's like the number of trees that you're training. The same with random forests. With deep learning, it's like number of like steps in the iteration, or you can think of the number of epochs or number of times you go through the data. And so you can see actually the error over time if you want. So that's what's in this table. For all the algorithms, it calculates variable importance in some way that makes sense to that algorithm. So for GBM, there's a particular way that people usually calculate variable importance. Same with, well, random forest, there's maybe a couple different ways. And then there's, for deep learning and geolearning, we have ways as well. So it will print out like the variable importances. And actually, this might be a good time for me to just show you what it looks like in Flow if we were to go over there. So I just opened up Flow. So this is like a blank flow. And since we've already done some modeling, I could click on this Get Models thing and it finds, okay, here's your model. And click on that, and you can kind of see some of the same stuff that we were looking at. So here's the scoring history. This is in terms of MSE. So orange is validation, and train is blue. So looks like we could probably train this GBM a little bit longer, because we did 100 trees, but it looks like if we were to train it more, the validation error would go down a little bit more. So another thing that I'll mention is that we added in this recent release is early stopping to all of our algorithms. So GBM in particular, you can overfit if you do too many trees. And so rather than, what we used to do is we put in, 500 trees, and then we go look at this and say, okay, right around like 200, that's probably where we should have stopped. Okay, that's something that we had to do over and over again. And so basically now we have a parameter that lets you turn on early stopping, and there's different criteria that you can say, like if the validation error doesn't go down over this many steps, then kill it. So we have that in all the algorithms, and there's different criteria that we use to determine that. So there's lots of like little things like that that we add that make it easier to just do machine learning. And so if there's something that we see people doing over and over again, we try to make that automatic. So one of the things would be plotting. Like maybe, we know after you train the model, you're going to want to look at the, maybe AUC and maybe the ROC curve. And so we just plot that for you automatically, so you don't have to, every single time do the same thing over and over again. So here's the ROC curve. That's for training metrics, is validation. Here's the variable importances, so now they just show up as a little graph. And then there's all this other stuff that's hidden by default, but you can peek at it. And then this might be a good time to mention, okay, so now if you have a model, how do you save the model? There's two ways that you can do that. So one is sort of the standard way of just serializing the model to disk. And it saves it as a binary file. And So you actually need to have H2O running to read that file back in. Same with like scikit-learn. If you pickle a model and then you save it, you need to like load scikit-learn first before you can, load that model in and make sense of it. So that's kind of similar. Same thing with R. So that's typically what I do because it's the easiest way to do that. And then there's another thing that's called the POJO. So POJO means plain old Java object. So this is actually very useful if you are going to take this model into production. So what you do is you save the POJO, and what this does is it spits out a bunch of Java code that represents your model. And now you have this file that's no longer dependent on H2O, and all you need to use it is to have Java. So you kind of separate the two. So you don't need to like start up an H2O cluster and then like have your test data coming in from customers or whatever and then score it. So what this does is it makes it really fast to score and to do predictions. So you can set it up to do streaming as well. There's like integration with things like storm bolts and things like that. These are all kind of things that I don't know that much about because I'm a statistician and I stick to the stuff. But so anyway, all of this stuff is obviously meant for companies to use it in production. So we have all of that stuff is very important to our staff. So anyway. I want to just check my time. I'm just going to spend a couple more minutes just to show you a couple more things. The other thing I'll just show you in Flow is if you want to just upload data, you just do this, like upload file, and you can upload it from S3 or wherever, and then you just click on the modeling and say, okay, I want to train like a deep learning model. Okay, so where's my training frame? Okay, here's the training frame, like here's maybe the validation frame. I can't remember what I called these, but you can name these. So these are like the default names that it will give if you don't specify anything. And then so as you see, I just scroll down and I have all of the features that I would have with the H2O deep learning function, but I can just click. So click on the response column. You can ignore columns. So this is where you choose the activation function, the hidden layers, like everything's there. Deep learning has a lot of parameters, so basically just scroll down to the end and would build a model and then it would start going. So anyway, that's how you do that in Flow. But let me just go back to the Python. And then I'll just mention a couple more things because I think we might be kind of getting done here. This is how you generate the model metrics on a test set. Take the model, there's a method called model_performance, and you pass it a new data set, which is test. And then once you have this performance object, you can grab like different metrics out of it. If you just want the AUC, you type perf.auc. All right. And so I mentioned I would just tell you how to do cross-validation. So basically all you have to do is there's an endfolds argument. So you're not writing any loops, you're not doing any of that on your own. Endfolds. So you just say endfolds equals like 5, and what it will do is it will do in parallel. Actually, we just changed this yesterday. We used to train the models in serial because it was actually still really fast, and when you're doing it serially, it's still using the entire cluster that it has available to it. However, it turns out a lot of people don't actually have big data. They just think they do. So like a lot of people, so we've kind of, now we're sort of like thinking about supporting more like small data problems. So we used to always think like, oh, it's more efficient for small data if we do it this way, but who cares? Like, this is not small data, this is big data. So now we realize that like, a lot of people have small data too. So we're trying to do things that are efficient for both big data and small data. And one of the changes that we just made the other day is, and this actually This has always been there, but we just, I guess, added the parameter to let the user do it. But so now it trains all the models in parallel, the cross-validation models. And it does that, so it would train 5 models here and score them all. And then it will train a final model on the data that you can use then to predict in the future. So when you get this model back, you would have the training metrics, and you can actually also pass a validation frame as well if you're, I don't know, really like excited about validation. So you could pass a validation frame, and then you can also do cross-validation, and then you'd have a lot of different metrics. And maybe you would want to do that to check, you know, that the cross-validation metrics kind of match up with the validation metrics, and that would make you feel like your stuff is working. So that's how you do n-folds. It's just that simple. So I'm not going to actually run this code. I'm just going to highlight just a few more things. So grid search is another thing that people do a lot of. And this is how you define a grid search in H2O. So for GBM, we're going to go over a grid of just a couple different tree sizes, or numbers of trees. And then the max depth parameter we're going to use as well, and then the learn rate. So we have 3 parameters, each with a few different values. So then maybe if you're not all familiar with what grid search is, it's basically just instead of training one model with particular parameters, you choose a sequence of parameters or a sequence of values for each parameter that you're interested in, and then look at all the combinations. So in this case, we have like 3 times 2 times 2, so 12 different models will be trained. So there's the grid search function here, and you basically just do it the same way. So you make this grid search object, and you pass in the hyperparameters, which is just a list of the things that you just defined, and then it will go off and train all those models. And then, let's see, and then, yeah, you do that by saying gs.train, if you call it gs. And then it will spit back all of the performance for the different models. So by default, it, I guess, prints out MSC, but maybe I don't care about MSC, I want to sort by like AUC, so let me just make that a little bit smaller. So now, I have the grid search object, and we have this thing called sort by, so you can sort by something. So sort by AUC, and so that the highest performing model is at the top. Oopsies. So that's this one here. So here's the parameters. So learn rate of 0.2, entries 100, and max depth is 5. That gave you 0.96 AUC. And as you can see, there's quite a difference here. And this is kind of a stupid example because number of trees is never probably going to be that much better if you're going to use 5 trees or 10 trees. But for all the, actually this is interesting. So the third model down, it actually only uses 50 trees. So you never know what you're going to get. So anyway, this is good to use that. Okay, so then, basically we're done, and yeah, so all the code is here. This is basically this last little bit that I might as well just say at this point because I'm not going to end early. So yeah, you want to get the model that has the best AUC. You can type that in, and then you can find the AUC, and then maybe take that best model and then go use it somewhere. Okay, so let me just sort of wrap things up. So one thing that I'll mention is, so one of the things that I've done at H2O is write this package called H2O Ensemble, which is basically, it's an R package right now, and it allows you to make ensembles of things. And so you can make an ensemble of, random forest, a deep neural net, and a bunch of other things. And it uses an algorithm called stacking, or superlearning, it's sometimes called. And what it does is it uses machine learning to figure out what the best combination of those models is. So rather than just averaging them together or some other thing that you could do, this is sort of the best way to ensemble, I guess, is in my opinion. So if you want to, get a bunch of performance by combining models together. This is a good way to do it. I'm writing the Python package right now. I was hoping maybe it would be done by today, but it's not. So anyway, that'll be in Python soon. So, maybe I'll come back and talk about that sometime in the future. And then let me just give you a few links where you can learn more. If you're a Kaggler, there's we put a bunch of H2O starter scripts on Kaggle. And then there's this guy, Mark, who works at H2O, who's our official competitive Kaggler. So basically he gets paid to do Kaggle, which is good because most people don't actually. So here's where to learn more. So we have all these different websites. We're trying to sort of consolidate all of our materials. We actually have a lot of different learning materials, but I think they need to be sort of consolidated better. And our docs, I will just say our docs are not as good as I'd like them to be. I don't want to say they suck, but we're working on improving them because right now there's just one big wall of text and it's hard to search and find things. So we're redoing our docs right now. So if you have any comments about the docs or anything about H2O, let me know. Okay, so we also have these booklets. I actually have the booklets here. So you can download these booklets. They're PDFs as well, but people seem to like the actual physical booklets too. So I'll lay those out. And we have them for all the algorithms, and then we have a Python one and an R one. So those go into really in depth, how did we implement the deep learning, or how did we do this and that. And so if you're interested in the details, that's what's in there. And then that's how to find me. So I'll answer any questions you may have. Yeah, thanks for having me.
Does anybody have any questions?
Hi, Erin. I'm David. Comfort, we exchanged emails a couple of times. So we were using H2O and R for the Kaggle Rosman project. And I guess I'm just trying to get a sense of how H2O and Python versus R is different, particularly around sort of factors.
The only thing that's really different is that the Python API is newer. So the R API has been around for a while, so it's probably has fewer bugs. But I don't know, a couple of months ago changed the Python API a little bit. So it originally used to look like the R API, where it would be H2O.gbm, and then you put in the parameters. But then we, after a million discussions about it, decided to make it more have a class of type, H2O, GBM, whatever, and make it more Pythonic. So now it sort of looks more like a regular Python package rather than looking like the clone of our R package. But in terms of functionality, when we're adding things in now, we add everything to both. So, so functionally they're the same. And there's been some work. I have not played around with this myself, but you can use H2O with the scikit-learn pipelines thing, and I don't quite know how that works, but I think we have some demos of it. But in terms of, just the differences, I think, if you have, one of the things that people like or companies like about using this at work is that they don't have to force everybody to use Python or R. So some people can develop in H2O and R, some people can develop in Python, but you produce the same things at the end, these models. And so it doesn't matter how you get there, and that might be, if you have people that like both, you can sort of just, or people that don't want to write code. Does that answer your question?
So at the end there, you just done a thing where we test all of these and came up with the models. How do I get it out of there and produce it, or should I be using it in H2O?
So how you can get it out,
Let's
there's...
repeat the question for everybody.
Oh yeah, sorry. So he says, once you've done all the modeling, how do you get the models out? And what do you, what are the next steps? So, and if it were me, if I were just doing research or something and this wasn't needing to go into production like tomorrow, I would just, there's an H2O.save model function. And so you save that, serializes the model to disk. And so it just saves everything that it needs right on the machine, and then the next time you need it, say you shut down H2O, so everything's in memory. So if you don't save your models, they go away. So, FYI. And if you are running H2O for a long time, and let's say something tragic happens and it, stops, and you have these models sitting in there, you might want to I don't want to scare people that your H2O cluster is going to go down, but it has happened where something weird happens and an H2O cluster goes down and somebody says, oh, I had all these models and I lost them all, and whatever. So, sorry, that's sort of boring reaction. Because people didn't know that they were in memory, so they thought oh, I'm just going to shut this down and then come back later. And so that's just something to be aware of, is that everything's in memory. So if you don't save it, then it doesn't exist anymore after you shut the H2O cluster down. So I would just save the models and then, shut it down or not shut it down. Doesn't really matter if it's just on your laptop or on a computer somewhere. And then when you're ready to, have those models again and use them, then you just load them in with the H2O.load model function.
Well, this is kind of related to that question. So you have the model exported now. Let's say you're putting it in production. You did a bunch of pre-processing and some of it magic. So
Yeah. So all of the.
Let's repeat the question.
Oh yeah. It's obviously my first time. So the question is, what about the pre-processing? And how do you sort of, I think I'm sort of interpolating other parts of your question, but how do you, if you're going to go to production and you did a bunch of pre-processing, how do you make that as part of your pipeline? So one way to do that is that you just have all the code that you used to process the data. Usually,
let's say you're in Java, you took the Java model.
Yeah.
And you go to production.
Well, so the data is expecting, the Java model is expecting, whatever sort of matrix or frame object it trained on. So if there's things that you've done before that to get to that point, then those same steps will have to be done in whatever pipeline you're creating. And so that's one area where we are working to fill that in more, I'll just say. So we want to do, I'll just say one part where we don't have a very strong pipelining place is for text data. So we're working right now to let's say you just want to throw a bunch of text data at H2O and you want it to do all the processing for you and then train the model and do all that stuff. So right now you still have to write the code to do the text processing and have that sort of in your pipeline like you would with any other machine learning library. And then once it's processed, hand it over to H2O as a matrix looking thing. So we're trying to, so right now when you train a model, it has to be on a data frame type of thing. So we're trying to extend where H2O begins to make it easier for you to put different types of data in, maybe images or text or things that people use a lot. So I would say we're working a lot on that right now, and part of what Matt Dowell, the data table guy, is doing is working on all the munging stuff and making sure that we can make H2O be the whole pipeline. So I don't know if that answers.
Exactly.
You had a question?
Yes, kind of along the same lines. You called or instantiated news Pojo
Yeah, Pojo.
while you were in Flow.
Yeah.
Were you able to do the same thing while you were in the Jupyter Notebook?
Yeah, so I think there's a function that says export Pojo or something like that. So in Flow, there's a button that'll let you preview the Pojo, and then you can export the Pojo. And then I think there's just a function in H2O H2O Python module or R module that will let you export the POJO. So yeah, so then it will spit out this Java file. So, sorry, I didn't repeat the question, but she was asking, how do you get the POJO, basically?
Similar, picking up on the theme of that, so you had built a model in the demo, and then you were able to go over to Flow and view graphs of all of the statistics and output of the model.
Yeah.
Could you do this in reverse and click a whole bunch of buttons in Flow and then have the code generated in the Jupyter Notebook?
Not yet, but people have asked us for that. So right now you can save a flow, so you can actually save your workflow, and that's basically what we would recommend right now. Yeah, what we do have is like when you're clicking buttons in Flow, it generates a bunch of REST calls, and it generates the same REST calls in R, so those are the same, but we don't have anything that takes the REST call and like translates it back into what R would have looked like. So you could, I've seen people do kind of like things like they have some way of getting all the REST calls and they put it in some sort of JavaScript application or something like that, and they kind of don't even use R. There's a lot of different angles that you can sort of get at what's going on, because if you can translate whatever you're doing into like receiving or sending REST calls, then it's all just, you can grab it. And anytime you do anything in R, like or Flow, there's a big log file that will say all the stuff that you've done and like compression statistics and stuff like that. And so, people mostly use that to debug if something goes wrong, but you can also see what all the calls are and sort of know what's going on that way.
Let me get back there.
Thank you very much for speaking to that. It's really informative. My question is more from a business model perspective. Is H2O looking to sort of pursue the Red Hat kind of model where you revenues through services and support? Are you going to is everything always going to be full open source? Would you ever hold any parts back?
That's a good question. Yeah, because I always wonder that myself. So basically right now, our business model is support. So we have like companies that pay us money, and they have support contracts, and then they, instead of maybe like hiring a data scientist, they will hire us to be their support on that. And so if something goes wrong or they don't know how to do something, they just like ask us and we tell them. We also will, for clients who want particular things, so we have like an insurance company that wanted us to add the Tweety distribution to the GBM. So we wrote that into their contract and they paid money for that, but then we put that in the open source. So I know that people have asked us to do things like specifically for them. So they said, we want this, but we don't want the open source to have it. Like we want it for ourselves, and we haven't done any of that. So the other thing is if you're a customer, we prioritize like your stuff. Like if you want something in there now, we'll put it in now rather than 2 months from now or whenever we feel like it. We do listen a lot to the open source community because they're, our non-customer paying open source people. So, because they're usually doing all the same stuff that our paid customers are doing. So if we see that a lot of people want something, we'll add it because we know that, that's probably somebody's going to ask us for it eventually. And then to answer your question about, is it always going to be open source or like what's going on with that? H2O is always going to be open source. So H2O, the machine learning, and everything that you see here and like all of the stuff that is machine learning is going to be open source. One thing that we're doing that's not open source is this thing called Steam, and it's kind of new, and it basically is a way to like deploy H2O easily, like with, I guess you could think about it like kind of like an Amazon Web Services, but for H2O type of thing. I don't actually know if that's a good description. Did you want to comment? wanted sort of like more, I guess, more turnkey solutions. So basically H2O with like a bow wrapped on it, you know.
There is more information on Steam on our website, so I'd say look for more information on its way, and for now, Erin hit it.
Yeah, and so, I mean, these discussions come up, you know, like, and Max will tell you, I'm always the one that's like, everything has to be open source all the time, like whatever, and, you know, I guess I understand, like, theoretically that we need to make money somehow, but I don't know. So yeah, there's the philosophy is that all of the math, all of the machine learning stuff will always be open source, and we shouldn't have to like close that down, because you see like now all of like, I mean, people don't want to pay for machine learning software. Like they want to use open source, and that's just what's happening now. So there's been a lot of like big companies releasing their open source, like TensorFlow and Google and all this stuff. So we think that, you know, we are just maybe like a little ahead of the curve on that, and we don't see like this being like like we tricked them all. Like now they're all using H2O. Now it costs money. And you know, and so I think that's what I know. And you know, I like open source, so I go where the open source goes. So.
All right, let's take maybe one or two more questions. Is that okay?
Yep.
All right.
So since you're an ensemble expert, could you talk a little bit about the relationship between how you do like optimizing ensembles at the same, like with hyperparameter optimization?
That's a good question. Yeah, so he says, or he asked, how do you basically optimize ensembles using like hyperparameter selection or something like that, like all at once, I guess. So, you know, in the typical single algorithm machine learning situation, we do a grid search or something like that, and we iterate over all the models, and then we pick the best one. With ensembles, it's kind of like there's not a whole lot of tuning parameters. So basically, the things that can change are which models you put in. And the idea with the superlearner or stacking method is that you can put in a bunch of like garbage and stuff that may or may not work, like just whatever, and it will just ignore that. If you know, kind of, it's a little bit like I don't know if this is a good analogy, but like in lasso regression, like you can put in a bunch of crap and it will just like regularize out all the crap. And so ensembles work a little bit the same way.
But you want to like optimize the amount of information from each of the models that you're going to include in the ensemble, but
right.
if you've already decided from your hyperparameters which models you're going to include,
well,
you can miss out on all the ones that might have information.
Yeah, so I mean, it's kind of an open question, like how to pick like what models to put in the ensemble, but my intuition is that they should be very diverse, so if you could put like one of each in. So if you go to like on the learn, so I'll just bring you to this website real quick, learn.h2o.ai. So this was our conference, which has now happened for the last 2 years, H2O World. So we have this training on here, and there's all different like little training things. So if you click on the ensembles training, this will give you kind of like an example of going through this process. And what happens in this example is it shows like I think maybe you only use 4 different learners in this one. So you put in like a random forest, a deep neural net, a GBM, and a GLM. And in this example, you see that like the random forest and the GBM are doing like pretty good, but the GLM is crap, and the deep learning is not very good either. So then you might think, okay, well, my ensemble's probably going to be better if I take away these like really bad models, and you know, let's see how that goes. And so what I do in this example is show that even though let's say the GLM is doing so much worse than the other algorithms, including it still overall gives better performance for the ensemble. Because the ensembles do best when there's very different algorithms in there. And so one thing that I think, it's kind of hard to get very different algorithms of the same, or very different models of the same algorithm. Maybe you can kind of do that with deep learning if you use different activation functions, or you want to kind of like make sure they're different. And so with GBM, I would take models that have like a column sample rate of very small and then very big. And like, so at least they're like as different as they can be for a GBM. And then I just put them all in there and just let it figure it out, basically. So I'm doing some work to try to have a better metric for like measuring the dissimilarity between the models, and so that might be predictive of how well the ensemble does. But I mean, the theory is that you just put in everything and then just let it do its thing. But you know, that's not super practical. You don't want to put in like 1 million models, and then if 900,000 of them are bad, why would you put that into production and have all these models running for no reason? So there is some aspect of like trimming the model down a little bit, like if you can, but that's other sort of work that I'm going to add to the ensemble, is coming up with more of like almost like an early stopping criteria thing, where you kind of just keep adding models until it's not smart to add them anymore. But I don't know how that works yet. So.
I had a question actually.
Yeah.
So H2O is distributed by name, right?
Yeah.
And so like one of the things is that it scales real well. So like how big? Like at what point have you guys been like, past 96,000 boxes, it's just garbage? How big's it gotten?
I don't know. What is it? Do you know, Max? It's like terabytes of data.
That would depend on the algorithm.
Yeah, it depends on the algorithm. I think if you have like really, really, really big data, like you might want to use like well, it depends on how wide it is too. Like if it's really wide, you're going to want to use like a GLM or deep learning and not a random forest or the GBM. But yeah, it depends on the data. I know we've tried it on like terabytes of data, and I guess a rule of thumb is like this is distributed, so there is overhead that you have when you know, it's better if you just have a high memory machine to use it. But if you don't, then get a bunch of machines. But it's always better to use fewer machines than it is to use more. But maybe it's not cheaper, so you don't care. And by better, I mean faster. But same accuracy.
Any more questions? We got one question way in the back.
Yeah, if a company were evaluating H2O as a data science suite, what alternatives would you recommend comparing it to?
Yeah, so he asked, who are your competitors, I think? Well, Solard is probably a good person to answer that question because he does a lot of benchmarking. So he's benchmarked H2O against, so probably the one that people compare us to the most often is the MLlib library in Spark, because it's kind of the same thing. It uses distributed data frames. It's meant for big data, whereas like scikit-learn is not really meant for big data, and none of the R packages are either, really. There's a couple that, I won't say all of them aren't, but I would say, yeah, compare it to MLlib and look at the accuracy of the models, because typically we do better, but
Yeah, and if I could just add, so that kind of depends on the culture of your company, right? So are you cool with open source? If so, then go grab some of the leading open source tools like us, MLlib, XGBoost, and run it on your own data and see what kind of results you get. Then, if your culture is not so open to open source, then maybe you're beholden to some other technology and you must use that for the comparison. In that case, we're still open source and we're happy to help you through that journey of comparison to see if you get any lift. We do get a lot of people coming from SaaS who say, You know, I can't iterate, it just takes too long. And then they supplant some component of SAS with H2O and then get licked. So that's kind of the beginning of the discussion, but there's no clear answer. I mean, it kind of depends because everyone's data is a little bit different and you're the experts on your data. And since we're open source, we you know, say go forward and go for it, right?
Yeah, I think it depends on, it depends on what your engineers like to use or what they're comfortable with. You know, if they're used to building their own algorithms, maybe they won't want to use a tool or something like that. I don't know. But you know, I've also done like a lot of benchmarking and benchmarked it against all of the open source tools that I used to use, and that's why I now work at H2O and why I left the company that I was working at, which I was benchmarking against a long time ago. And so I'm biased, but yeah, I think just try it and just see if it makes sense in your workflow, and
Oh, hey, let's say. One quick note, guys, we need Python speakers.
Yes.
We need Python speakers. We need some of y'all. I want to know if you guys want to do like 10-minute lightning talks at the next meetup, or community members to speak. Message me, email me. We need you guys to come out here and speak.
If anybody wants a coffee or anything, feel free to help yourself.
You're the funny guy. Yes. Hello, everybody. So welcome to the first Python Data Science Meetup of 2016. Woo! So I appreciate it. Thank you. I don't know how these things work. Going to get just a few small things kicked off. Quick show of hands. How many of you are on the datascience.la mailing list? Okay, most of you happen to hear it. For those of you that aren't, at some point I'm going to get tired of like copy pasting the message to the meetup boards and all that, and the only place I'm going to send the meetup information is the datascience.la mailing list. So eventually you're going to want to get on that. So I had a couple of other things. So there's the first meetup. We've got a second meetup scheduled, not for the Python Data Science meetup. We have a meetup scheduled for next Monday. If you want to go, it's on the west side. It's at ms.com, and it is. We have an Apache maintainer who is one of the main architects of Apache Tahoe, and he will be speaking about basically how they're building a high-end columnar distributed data store on HDFS and whether such a thing is even possible or not. So that's next Monday. You can still sign up on Eventbrite. You can find out about it on our website, which is datascience.la. So the next thing I wanted to do is we have somebody from UCLA to talk about UCLA's DataFest. So if I could call her up. So real quick, DataFest is a thing that I've gone to now 2 years. It's super fun. You should do it, but I'm not going to steal more of her thunder.
Hi everyone. Hello. Okay, I would like to introduce myself as the undergraduate committee member of the 6th annual DataFest hosted by UCLA. And DataFest is a weekend-long data analysis competition structured like a hackathon, but differs as teams from local universities work with the datasets to provide tangible business insights from the data at hand. Last year was our largest event to date, and we hope to emulate the success again this year. As a non-profit statistics club coordinates this event, we really appreciate and acknowledge corporate and private sponsorship and support as an integral part of our program. Sponsoring DataFest gives your company the opportunity to share its brand with some of the highest achieving students in Southern California. Teams will represent UCLA, USC, Cal Poly Pomona, Cal Poly San Luis Obispo, Cal State Long Beach, UC Riverside, and possibly more. Though we appeal to individuals with statistics background, we also attract students from business, economics, accounting, and social science departments. Bring a diverse host of talents to our event. Previous competitors have gone on to hold analytics positions at high-profile companies like LinkedIn, Salesforce, Deloitte, Experian, and more. All sponsorship will be given an opportunity to share promotional and recruiting materials and swag during the event. So if your company is interested in DataFest and want to take advantage of this opportunity, please feel free to get one of these papers with all our information, and I will put those in the back of the table so you guys can grab it. Thank you so much for your time, and I really appreciate like we can work sooner. Thank you.
Can everybody hear me without magnification? All right, good. So I want y'all to look around what a really cool venue we're at. Like we're at the Venice Art Center in Lincoln. Like, this is really cool. This isn't like when I lived in Nashville, Tennessee, meetups weren't happening in awesome spaces like this. And the reason we have such a cool space with great food, I know we even have veggie trays, which is amazing for a meetup, like, is because of our sponsors. I wanted to thank Open Mail, and I wanted to give them an opportunity to say something. So thank you, Open Mail.
Hey everybody, just want to thank everybody for coming out. We at Open Mail, we share the interest of promoting Python and data science and the intersection of those two within the community in Los Angeles. So we're really happy that everybody's been able to come out, and the PyData meetup's just been growing by leaps and bounds. I want to thank the speaker Erin for coming down, and we are hiring. So if anybody is looking for if anybody's looking for a collegial environment, Python data stack, and a lot of great people to work with, definitely grab anybody who you see as an Open Mail name tag on and ask them about Open Mail. Thank you.
All right, so we're going to get now to the real meat of this meetup. Real quick show of hands, y'all came here. Have you used H2O? Are you familiar with H2O, or is this brand new to you? Okay, so you've got a lot of new people to teach. Pretty excited. So we're very lucky. So Erin LeDell is a statistician and machine learning scientist at H2O. She's the main author of H2O Ensemble. Before joining H2O, she was the principal data scientist at Wise and at Marvin Mobile Security. She's the founder of Data Scientific Incorporated. She has a PhD in biostats with a designated emphasis in computational science and engineering from UC Berkeley, a way better school than I could ever get into. Her research focuses on ensemble machine learning, learning from imbalanced binary outcome data, influence curve-based variance estimation, and statistical computing. So everybody give her a warm welcome. It's Erin LeDell.
All right. Oh, yeah, okay. With them to, make sure everything is sort of legit. All right, so here's the agenda. I'm just going to explain what H2O is, and then I'm going to talk about the Python module, and then I'm going to do the demo. Okay. So I've already explained this a little bit, but this is kind of like the high-level summary. It's H2O is written in Java, and that's one of the reasons why it's fast. So typically, high-performance machine learning libraries are either written in C++ or Java, maybe some other languages as well. And essentially, how it works is let me get to that. I don't want to get ahead of myself. So anyway, APIs and our Python Scala. All right. So the whole this is just kind of an overview slide. So the whole point is that you shouldn't have to sample your data. You have all this big data that you've probably spend a lot of time getting, and then what ends up happening is that people have now too much data and they can't train their models, and so you end up sampling out of this big data, so you don't really have big data anymore. So the idea with H2O is you don't have to sample your data, and then part of our other philosophy is that we want to have all of the sort of cutting edge algorithms. So a lot of the machine learning algorithms have been around for a while, but there's lots of different things that lots of developments that get added over time, so there's maybe new optimization methods or new ways of parallelizing things, so we're always trying to have sort of like the cutting edge of the algorithms that are out there. So here's just sort of an overview about the algorithms that we currently have. So it's kind of a smattering of different things, so we have mostly supervised learning algorithms, but some unsupervised stuff. We have kind of like what I would call like the big four like algorithms that people use a lot. They use random forest, GBM, gradient boosting machine, GLM is still really widely used, and deep learning. So we have a function called deep learning, which I think probably could be more aptly named to like say what kind of deep learning it is, because there's all different types of deep learning algorithms. So it's a multi-layer feed-forward neural network. So I don't know if that, if any of you guys are familiar with all the different deep learning algorithms, but basically this is one that works well and works fast on CPUs. So deep learning, a lot of the stuff is written geared towards GPUs right now, and so this is one that still actually works really well on the CPU and is quite fast. So maybe just a couple other things. So we have a lot of different solvers. So something that we'd like to do is have different optimization routines that you can use in each of these algorithms. So we don't just make you use a particular one. And if some of you are familiar with R, there's somebody called Matt Dowell. All right, thank you for having me. I came all the way from Northern California, where it's equally as rainy. I had this dream that I was going to come to Venice Beach and it was going to be beautiful. And it's still beautiful. Yeah. So yeah, I guess it's good that we're getting rain in California, so I shouldn't complain. So. Anyway, so this is an intro to H2O and Python. So presumably a lot of you guys are already using Python, and maybe if you're doing machine learning, you're using like scikit-learn or some of these other libraries that are popular. So hopefully by the end of this talk, you'll have an idea about what H2O is and how it compares to maybe what you're already using. And then, so the first half of the talk will be slides, and then I'll go through an IPython notebook, and I'll point you guys to where that is, and if you want to like follow along and do the IPython notebook on your own machine, you can do that, or you can just watch and take it home for later. So, okay, so I already got an introduction, so I won't really talk about this stuff too much. And before I forget, I just want to grab my phone so I can time myself. Talk too long. So anyways, yeah, so I work at H2O. I've been there for about a half a year. So I recently graduated from Berkeley in May. So, but kind of before that, I had like another career as a computer programmer, and before that I was a mathematician. And then I, learned about machine learning, and then my whole life has just been about machine learning basically ever since, because I love it so much. I am sort of more of an R person. I hate to say an R person or Python person, because I think we're like beyond that at this point, but I'll say as a statistician, I was using R a lot for the last 4 or 5 years. But the first language I ever learned was Python, so I've kind of been using both for a long time. So, all right, so what is H2O? So first of all, there's H2O the company, and then there's H2O the software. The company actually used to have a different name. We used to be called Hexadata, which was spelled 0xData, which nobody could pronounce that, and it was just, I don't know, people didn't like it. So anyway, we changed our name. Now we're just H2O, and so we've been around since 2012, and we're based in Mountain View, and the sort of people that started it were loosely affiliated with Stanford, but there were some people from Purdue and kind of these like mishmash of people that came together and started this company. So H2O, the software, is open source, and that's probably the main reason that I work at H2O. I'm actually not very interested in any non-open source software at this point. I think that's like the old way of doing things. So that was really important to me, and I don't know if you guys are that passionate about open source as much as I am, but that's a big win for me. So it's open source. We try to make it easy for people to use, and part of that is that we make APIs in R and Python. There's a Scala API. It works on Spark and Hadoop. So originally it was written for Hadoop because Spark didn't exist, but then Spark got popular, and so we actually rewrote all of H2O from scratch so that it would work better with Spark. And that was H2O 3.0, which was released over the summer. So that's probably that, some of you are actually, nobody really raised their hands, did you? Anyone who used H2O? Okay, so anyway, if you were using H2O 2.0, there were some changes that we made, and so it's a little bit different now. But so the last thing is we also have a web interface. So if you really just have a hard day and you just don't feel like writing any code, you can just click and do everything from the web, the same as that you can do from the different APIs. And so the whole point of H2O is that it's not just like another, scikit-learn or another machine learning library. The whole point is that we've rewritten all of these algorithms from scratch so that they work in this distributed framework. So I'll explain more about that later. So I just wanted to mention just a couple more things about the company. These are the founders. Are there any Java people in here, or people that identify with Java in any way? No? Okay. Then if you did this, apparently Cliff Click, I'm not really from a Java background, but apparently he's a famous Java person. And so if you were a Java person, you might know him. But he's sort of maybe like if you're an R person, the Hadley Wickham of Java. I don't know. I don't know who the Python equivalent would be. But anyway, he basically did a whole bunch of research that made Java actually be performant and fast. So in the 90s, he got Java to work, and so he developed the Java hotspot compiler, which is kind of a new way of doing things. So he's sort of like the brains behind all of the underlying architecture to the system and why it's so fast and why it's good. So, and then if you do have any sort of machine learning background, you might be familiar with some of these names. So Trevor Hastie and Rob Titrani have a famous machine learning book that's called The Elements of Statistical Learning, and they have another one that I think it's called Intro to Statistical Learning or something like that. So they're pretty famous in the machine learning community. And then Dr. Stephen Boyd, he's famous sort of for different things, but he's more of an optimization guy. So these are our scientific advisors. We work with them to make sure we've implemented a lot of their algorithms, and so we work